Hello, everyone. Welcome to the 2016 Global Dialogue on Waste. We're proud to be disseminating high-quality knowledge through the Global Dialogues on Waste consecutively for the fourth year. Over the past 4 months, we've explored the role of managing waste and improving well-being and quality of our planet on our quality of life on our lonely planet. And we discussed how to mitigate the ocean plastic pollution, climate change, and all the consequences of those global challenges. We also made a very strong case for waste management as a high priority issue and a global challenge itself. We heard from artists, professors, scientists, and other leaders who are providing solutions to and through waste over the past 4 months. And now this journey comes to an end with today's panel. And as we look forward to a new year, we'll keep publishing high quality knowledge on our website and engage various leaders through Twitter chats. Next year, we'll publish the waste influencers list of individuals and organizations. The waste influencers list identifies 30 individuals and 30 organizations who are effectively sharing their knowledge and stories through social media. Our next Global Dialogue on Waste in 2017 will be different. To know what will be different and when it will start, subscribe to our newsletter and follow us on social media. For today's panel, we have two very well-known professors and a scientist and a young engineer to moderate the discussion. I'll let Demetra Tsiamis, the Associate Director of Earth Engineering Center at City College of New York, to take it from here. So, Demetra.
Thank you, Ranjit. Thank you. So before we begin, I'd like to ask each of the panelists to provide a brief introduction of who they are. I'll start off, as is mentioned, I'm Demetra Tsiamis. I'm the Associate Director of the Earth Engineering Center at City College of New York. And what our center does is industry-applied research on sustainable waste management and waste conversion technologies. So I'd like to pass this over to Professor Castaldi.
Hello, I'm Professor Castaldi. I am appointed in the Chemical Engineering Department in City College of New York. I'm the director of the Earth Engineering Center at City College of New York, and the primary research focus that we have is connected with fundamental information that we develop, as well as industrial projects that we work on, mostly in the thermal conversion of wastes, focusing on pyrolysis and gasification.
Professor Themelis.
Good morning. I'm glad to be joining Be Waste Wise. I'm Nickolas Themelis. I'm director of the Earth Engineering Center, a sister organization to the one you described, the one you belong, at Columbia University. And I'm also chair of the Global WTRT Council, the Waste to Energy Research and Technology Council.
Dr. Mohan.
Hello, it's a pleasure speaking on Be Waste Wise. I am Dr. Venkata Mohan. I am working as principal scientist in Indian Institute of Chemical Technology, Hyderabad, a premier research institute under Council for Scientific and Industrial Research. And basically, I am working with Bioengineering Environmental Sciences Department, where we do basic and applied research pertaining to environment in the interface of biotechnology. My major focus of research is on sustainable waste remediation. We try to use waste as a potential feedstock and to recover chemicals as well as fuels. So in a biorefinery format.
Thank you. So to start off our discussion, I thought that we'd first provide some background to the audience on the specific technologies that we'll be discussing today, specifically biological treatment of waste, as well as thermal treatment, which includes waste to energy, gasification, and pyrolysis. So my question to the panelists is, I'd like to ask you to elaborate on the current research that you're doing in this area, and how do you see your waste technology contributing to the overall picture of sustainable waste management? Professor Castaldi, do you want to begin?
Sure, I'll begin. So as I said at the beginning, we focus on pyrolysis and gasification technologies, and we mostly look at how those technologies can convert waste materials to things other than carbon dioxide, water, and heat. And the key there is that by using a pyrolysis technology or a gasification technology, it has a limited amount of air or oxygen that's brought into those systems. And what that allows these technologies to do is produce a synthesis gas. And this synthesis gas is primarily carbon monoxide or hydrogen. And that CO or hydrogen can then be utilized to make power or make fuels, liquid fuels, which a lot of companies are trying to do, or of course, make other types of products. For example, synthesis gas is one of the primary building blocks for things like plastics. And so in terms of sustainable waste management, by utilizing technologies like pyrolysis and gasification, there is a platform that can be developed where a waste material that has organics, carbon, hydrogen, oxygen, and plastics and paper can be put through this technology, yielding a synthesis gas, that then that synthesis gas can go across different options, either to be further processed to make a product like plastic, to be further processed to make fuels like a liquid fuel and be distributed a little bit more easily in local or in rural environments, or to be directly combusted and generate power. So it's one way, if you will, to offset the use of fossil-based materials, or what we might think of as materials and resources that have a limited lifetime. And here, as we produce garbage and waste, of course we want to extract all of the recyclables and try to do as much composting with the pure organics, food waste, and so on. But non-recycled, contaminated types of wastes are very well suited to go through these devices to then make some products that the world can use.
Dr. Mohan, would you like to explain some more of your research and how you see it contributing to sustainable waste management overall?
Dr. Mohan?
Yeah. Hello. No, we are working on basically waste remediation, advanced waste remediation methods by using biological platform. The basic objective of our research is to use as a potential feedstock to recover carbon as well as nutrients by acidogenic fermentation. Acidogenic process is our focal process where we try to process the waste and convert it into hydrogen in the first stage. Along with hydrogen, we will be getting as a volatile fatty acids, which will be recovered as a platform chemicals for many of the organic synthesis. So the hydrogen, once we extract from the waste, and the volatile fatty acids, along with COD, we have about 50% of carbon. We will try to integrate with bioelectrogenesis, which is a hybrid process between acidogenesis as well as electrogenesis, so that the carbon will be converted into electricity. So by this way, in the second stage, we will be recovering about 80% of carbon along with the nutrients. So we'll be able to recover two forms of energies along with platform chemicals. In the third stage, the organic fraction present in the wastewater will be reduced by 90% by using photosynthetic, where the 20% of carbon in a mixotrophic mode will be converted into biomass as well as lipids. So in a biorefinery framework, we are trying to address the holistic problem for waste and integrating with the remediation. So by way of this, there is no need for going carbon reduction or carbon removal up to methane in a single stage. By way of going to methane, we are losing all the carbon material. So we are trying to refine the waste, the different process, and trying to recover value-added products as well as energy. So in this direction, we are trying to develop various models self-sustained models, closed loop models, so that it can take the material waste and produce various raw materials, including bioplastics, fatty acids, as well as lipids. So we are trying to close the loop, remediated waste or wastewater, along with reduction in CO2 to a certain extent. So in this direction, we are trying to address the waste issue in a circular economy by circular economy, and trying to put waste as a futuristic feedstock in the place of fossils using for our energy as well as materials. So most of the material energy requirement can be addressed with waste. That is our basic objective. In this direction, we are working on various waste biorefinery models.
Very interesting. And Professor Themelis, how do you see waste to energy contributing to this overall picture of sustainable waste?
I'd like to mention that our center is concerned with all means of sustainable waste management, starting with recycling, composting, and waste to energy. But today my subject is waste to energy, and the area that we are working on is what's considered the conventional, the traditional means, which is combustion of municipal solid waste and other waste directly, and then using the heat of the combustion gases to make steam, and the steam then produce electricity, and some of it can be used for district heating or industrial processing. The means which are used for what we call now waste to energy, although waste to energy would include other means of making fuels, but right now we're talking about combustion with energy recovery, are basic two. The dominant one is combustion on a moving grade. It's used in over 800 plants in the world already. And the second one is one who has been developed the last 10 years, mostly in China, which is called circulating fluid bed combustion. They are efficient in terms of recovery energy, but if you could make, of course, a fuel from some of the waste, then the thermal efficiency of using a fuel is higher than the thermal efficiency of using steam.
Very interesting.
Electricity.
Thank you. So, as you mentioned, some conventional technologies that have been around and have now touched upon more recent developments. We'll get to that in just a bit. I just have a follow-up question for all the panelists regarding the type of waste that these technologies can process. Because as we all know, our waste is made up of a diverse array of materials. And so some would argue waste management has to be multifaceted because one method may not be able to handle all the materials in our waste. So what materials in our waste stream can your technology that you work with target, and what final products can they yield? I believe some of that has been mentioned, but if you could just reiterate that for the audience.
You're asking someone in particular?
It's open to all the panelists. If we want to go in order, Professor Castaldi can start first, or whoever.
Well, maybe I should say, because the combustion with energy recovery can burn everything. Metals, of course, do not make energy, but you can recover the metals from the ash. So the other gentlemen, the other participants can talk about the specific streams or the streams they would like to see as feedstock to their processes.
Let me add on that. Let me just add on that, because as Professor Themelis has mentioned, it's the thermal process, the combustion, can handle all the different wastes. The gasification and pyrolysis systems, while theoretically they can process all different wastes, they are much better suited for what I would consider purer streams. So of course we want to extract all of the valuables that we can, recycle as much as we can, take out the non-combustibles, glass and metal and so on. But if we have a very mixed stream because the gasification and pyrolysis systems try to operate in a very narrow window of, let's call it temperature, for example, that the different types of components and materials that make up the waste prefer different optimal temperatures if you want to make a synthesis gas. So while theoretically you could put in all of the different non-recycled waste components, it would not operate as well as a combustion system, and it would be preferred to take, say, mostly plastic or mostly paper or mostly wood, because then the system will be able to operate within that narrow regime. It will have a little bit more of a consistent feedstock, and then will be a little bit more manageable and efficient.
So coming to our process, basically ours is a biological process. So we are using three kinds of waste: liquid, solid, as well as gaseous streams. Coming to liquids, any wastewater which have COD more than 5,000 mg per liter up to lakhs of COD mg per liter can be used for this process, which I have explained earlier. But coming to solid waste, particularly municipal waste, the biogenic fraction will be more suitable for converting it into bio-based products by biological process. Gaseous streams, right now we are working with CO2 creation by photosynthetic integrated with electrochemical methods. So our process can take up the carbon if it's more biodegradable. Degradable means BOD by CO, COD by BOD ratio more than 0.2, along with some amount of nutrients. So right now we are trying to use the mixture of municipal waste, biogenic municipal waste with food as market waste, vegetables. So that by acidogenic fermentation, we are trying to produce hydrogen. With this process, we are trying to set up a pilot plant, 10 metric cube pilot plant at our IICT, process to industry. This project was funded by Ministry of New and Renewable Energy, Government of India. By end of next October, we are trying to demonstrate the process for hydrogen production, particularly from biogenic municipal waste.
Okay. So to now switch the discussion topic to the title of this panel, which is actually the future of these technologies, I'd like to ask the panelists, what is the current status of your technology that you work with in terms of the successes as well as the challenges that you see the industry facing? And where do you see your technology in terms of both development and application within the next decade?
Demetra, it would be helpful if you appoint somebody, you know, otherwise we
Professor Castaldi, let's start with you.
Sure. For the future of gasification pyrolysis, this is a difficult question for a few reasons. One is gasification and pyrolysis systems have been developed in the past. If you look at a classic gasification system, it is the gasification of coal, and it has been developed in very, very successfully in South Africa, called the Sasol project, where they take coal and they do gasification and they yield a synthesis gas and they make diesel fuel. And they've been doing this for 50 years. Many, if not most, gasification systems are modeled after this type of technology. Pyrolysis systems, of course, have no oxygen at all, and they are completely endothermic, so there has to be an external form of heat being brought to them. Now, again, once you think about it, how things have been developed in the past and how the systems have been adapted to treat or process waste streams, they work. The big problem that has been connected with pyrolysis and gasification systems are, I would say, three prongs. The first one is, as I spoke about, the stream should be more or less pure, either all plastic, all wood, or something like this. The second one is the feeding system needs to be robust enough, because as we know, waste comes in very different sizes, shapes, densities, and so on, moisture contents, and therefore to have a good continuous feed into the process is paramount. And then finally, of course, is what is the quality of that final product gas, that synthesis gas. And of course, they're related. If I have a varying feed stream, I'll have varying gas. If I cannot feed it properly at the constant rate, I'll have a varying gas. So I say all of this because to your question of what is the future of these technologies, I would say it appears that these technologies will start to take more of a foothold in the future, primarily because waste streams are getting a little bit purer, at least in developed countries. The extraction of valuable materials in the waste, such as plastics and glass and so on, paper, have rendered streams to become a little bit more uniform. And secondly, the advent of what I would consider very fast feedback control systems and solid state sensors and controllers enable these systems to be a little bit more controllable and operate a little bit more uniformly. One of the, I would call it, success stories to date is a process called the Enerchem process, where they have a commercial scale facility operating in Edmonton, where they have been able to take waste that has been already pre-processed in terms of taking out the valuables, the glass, the plastics, the metals, and so on. And that residual then goes into a gasifier that makes a synthesis gas that then goes through a catalytic process that makes methanol. And the demonstration of that system on a commercial scale has been enabled because of the sorting processes upstream that have been able to make that refuse-derived fuel a little bit more consistent. And of course, the feedback control systems in terms of how the gases are being released from the gasifier and put toward the catalytic system, and how other co-reactants need to adjust. So there's been a large development in the past. It has been definitely associated with a lot of failures, a very number of high-profile failures, but that is not because of the technology in terms of gasification or pyrolysis. It's usually because of the types of streams that they were trying to process and or what products they were trying to make. And I think those lessons learned are being well put to use with new companies and new ideas that are coming forward. So I would say it would be a slow path in terms of continued development, because pyrolysis and gasification systems have a history of being risky, but there have been a number of high-profile successes that I think are going to start to gain a little bit more traction.
Okay. Professor Themelis?
Yeah, one item we have discussed, and Professor Castaldi will discuss later on, is pyrolysis of plastics, because in that case you can get an oil instead of a synthesis gas. You can get an oil, and as we have studied that, and we're still studying it, and we have not found a process in the United States that can do that. And plastics are a good feedstock, because right now 80% of them go to landfills in the United States. But in India, there is a process called Pyrocrat, P-Y-R-O-Crat, Pyrocrat, that they claim they have 17 plants to turn plastics into oil. And we're investigating that because possibly that can be moved to other developing countries. Now, coming back to my subject, two things have kept the development of waste to energy in globally. One is the capital costs of plants is high, relatively high, and so paying it back on a per ton processed basis results in a high gate fee, required an entry fee. That was the people who bring a ton, they may have to put right now something like $70 to pay just for the capital charge. So that, of course, makes waste to energy less attractive from an economic point of view and neglecting the environmental costs to landfilling. So that's the first thing we are addressing. How can we decrease the capital cost of waste to energy plants? And China, interestingly enough, has been able to do it. They built several plants in recent years at about 1/3 of the capital cost of the American and European and Japanese plants. So we are looking at that because that could encourage India, for instance, to build more plants. They're building 2. Now, the other thing is that the bad image that the people have of waste to energy plants. They're power plants, but they consider them still incinerators. And it's not correct because in the United States, we have, let's say, 80 waste to energy plants, and we have about 1,500 incinerators of different types. So you should not be confused. So we're working on that subject also in terms to show that the emissions from these plants are minute and they should not be held against them. So these are the problems they have. Publicity, public relations, and capital costs.
Okay, and Dr. Mohan?
Yeah, the current status of the process, broadly we are working on 3 areas, 3 processes: aerobic process, integrated with acidogenesis and methanogenesis, bioelectrogenesis, and photosynthesis process. Coming to the first anaerobic process, the basic objective of our research is to integrate with the effluent treatment plant, because ETP operators or industries, they will be more happy if we can redesign it to lesser extent rather than going for new reactors. So we are trying to redesign the aerobic process to acidogenesis in order to produce hydrogen. So in this direction, we are setting up a pilot plant capacity where it can take liquid waste or biogenic solid waste to produce hydrogen. The major challenge with this process is the economics. When we consider hydrogen, it will be 50 to 20% higher than the market cost. So then we try to address the issue by taking out the effluent coming from hydrogen reactor, which contains a lot of volatile fat acids. So these volatile fat acids will form as a potential chemicals for many other processes, such as acetic acid or propionic acid, butyric acid. So when we integrate the process by producing hydrogen with recovering the fatty acids, then the whole process is economically viable. So right now we are addressing the acidogenesis process by integrated approach. So apart from that, in an integrated way, we are trying to link up the effluent coming from hydrogen reactor process, such as anoxic process, to consume the fatty acids by aerobic bacteria into polyhydroxyalkylate, a kind of bioplastic, so that we can gain more of value addition in the closed loop operation. So this, the first process we have demonstrated at 50 liters and right now at 10 meter cube capacity. The second process we are demonstrating to industry at 100 liter capacity process by electrogenesis. We are trying to integrate with the ASP, activated surge process in effluent treatment plant, with a light modification in the design so that we can induce the electrodes, we can increase the process efficiency, at the same time we can recover the energy. The third process, photosynthesis process, has significant limitations with respect to biomass production. Biomass production, when we go with the CO2 sequestration, it's autotrophic mode of operation. So we are trying to address the biomass productivity issue by considering the mixotrophic mode of operation, where it can take carbon from atmosphere as well as from liquid streams. So we are trying to productivity, whereby we can also increase the lipid synthesis. By this way, we are at present our technologies. The first technology of hydrogen production, it's at pilot scale. The second one we are already translating to the industry, and third process we are trying to make up at 100-liter capacity with 3 different reactor design. So current status, the final objective is to integrate with the effluent treatment plant. Easily go into the cycle.
Okay, thank you. So in the interest of time, I'm going to have a two-part question for my last question in this panel, which touches upon something important that Professor Themelis brought up, which is this idea of public perception of these waste management techniques. So as Professor Themelis had mentioned, there is public concern at times regarding environmental impact and health risks associated with thermal treatment of waste. So my question to the panelists is, what research is being done in terms of environmental impact, or what is known in terms of environmental impact and health risk with your technology? And the second part of that question is also waste factors such as the geography of a community, the economics of the community, as well as the social fabric. So where do you see your technologies being implemented? Is it in agricultural communities or developed metropolises? So we'll just start off again with Professor Castaldi. If you can address both the environmental aspect as well as where do you see your technology being applied?
Okay, thank you, Demetra. That's actually a very important question. A couple of things. One is, I should say, in terms of the environmental impacts, it's, a gasification or pyrolysis system is a thermal treatment system, so therefore it does have emissions. The emissions are slightly different than what you might find in a combustion system, as Professor Themelis has mentioned. However, they are regulated. They meet the regulations that standard organizations put out, such as the US EPA, the EU BREF regulations. And so the key is that there are emissions. They are below regulated standards, and that opens up a bigger discussion as to what is acceptable in terms of emissions. And, if we believe and, follow our policymakers and our decision makers and these organizations that scientifically set regulations matched with human health risks, then these systems should be acceptable, just like the emissions from a car, just like the emissions from a power plant, and so on. The social aspect is a little bit different, and that touches upon, I think, a few things. I just want to comment a little bit in the social aspect. We, as you know, Demetra, we had put on a conference over at City College that looked at sustainable waste management in megacities, and it basically touched upon the waste hierarchy from reuse and reduction all the way down to landfilling. And one of the sort of themes that came out of that was twofold. One is people's behavior needs to change. And that is on two sides. One is many people think that it's possible to reuse and recycle all waste. And so therefore, there's no need for any disposal options, whether that be a thermal disposal or landfilling. The other side of that sort of theme that came out in behavior of people is the focus and the care. When you ask and take surveys of most people about their sensitivity, their feeling toward the environment, it usually comes up at a very high level. They are aware of environmental issues. They want to have the least amount of impact on the environment that they can. But when you connect it to the actual garbage that they generate, there seems to be a disconnect. And so one of the things that we found in this conference was that people in New York City are very knowledgeable about what to do with the waste. However, many of them choose not to do it. So the social aspect of this, gasification technologies and pyrolysis technologies in some respects are considered more benign than combustion, or as Themelis says, incineration systems. However, others see that as what they call disguised incineration. And the key, I think, question about the social acceptance of any of these things is how is the people's behavior that are generating this material going to change to ensure that they get put into the proper processes, whether that be reuse or recycling, or whether it be disposal in a thermal system or disposal in a modern, well-designed landfill. This is the way we will manage this waste at the scale that it's generated.
Before we go on, I just want to let the remaining panelists know that we have 10 minutes left, so please be mindful as we want to get to both Professor Themelis as well as Dr. Mohan.
Yes, well, we have tackled, you want me first?
Yes.
Yeah, please.
Okay. We have tackled the matter of public perception quite a lot in our research at Columbia University. Recently, we made the study was just dioxins. Dioxins always mentioned as the big problem. We found out that dioxins were a minute fraction from waste to energy plants that was something like 3 grams per year versus 3,000 from the US as a whole. We're doing a study like that for China, and we're making another study for mercury now, the same inventory. I should say that the people, when they talk about emissions, they compare with recycling, which, as Professor Castaldi mentioned, in many cases it's not possible to recycle. I mean, if it could be done, let's do it. But they have to compare it with landfill, and landfills extend over hectares of land. It's very difficult to collect the gases. Regarding where combustion with energy recovery would apply, I would say everywhere, but up to now has been out of the reach economically for countries like India and countries that have relatively low GDP. But the Chinese, in the last few years, they built something like 30 waste to energy plants a year, although they have a very relatively low GDP, and they've been able to do it by a less cost technology. So these are we think that this combustion with energy has to apply on a large scale. You have to have, let's say, over 300,000 tons of waste per year to apply it, which means cities and megacities.
All right, and Dr. Mohan?
Yeah, with respect to environmental impact and health risk, I would like to add here that the process which we are using is biological, and biological means sustainable. So trying to use biological routes to valorize the waste. Traditionally, the biomethanogen process, where at the end of the pipe process, we will be getting methane. Methane again is a. So our process try to address to recover carbon in a refined way to more value-added products instead of going to a methane at the end. So this will give the sustainability to the process and also reduce the carbon footprints to maximum extent. And moreover, there is no much of energy inputs to the aerobic process. Basically, it's anaerobic process. So the reduction of carbon load, carbon footprints, and recovery of carbon for useful products will have the environmental sustainability, and we can also counter the health risk. At the same time, remediation is also integral part. So I would like to say sustainable waste remediation platforms.
Okay. So I think, is that a time, Ranjit, or should we keep going? Because I'm sure we can keep talking about this.
Well, one thing that should be made clear, I think it was hinted at by the speakers, is that you have to have different streams of waste for the different processes, like pyrolysis and gasification. Pyrolysis is on plastics, really. Gasification can be on more things, but it's better not to have a lot of water, let's say. And the other thing is the process of Professor Mohan. This can be applicable to green waste and food waste. And all of these have to be separated and provided to the plants that are going to treat them as feedstock. And that depends on the willingness of the citizens and of the communities to do this separation and collection.
Any other concluding remarks from Professor Castaldi or Dr. Mohan?
Sure.
Yeah.
I will just conclude very briefly that the thermal systems that have been developed, combustion, gasification, and pyrolysis and others, are well known. And the key is where does it make sense, either economically, or where does it make sense environmentally. And that is very important because it depends on not only, of course, the development status of a country, but also the types of waste streams that are available. Very wet wastes are not really well suited for thermal processes, but they are well suited for biological processes. So it's these considerations that need to be always in the minds of policymakers, decision makers, and quite honestly, the public, to ensure that the waste that we generate at the scale that we generate is managed properly.
So I would like to conclude that waste is not waste anymore, and waste is a resource. So government has to take up regulatory policies in order to make this process coming to the value chain. So by these platforms to come into the existence, it has to be encouraged with SMEs, MMEs, as well as young entrepreneurs in order to make this more visible and to come into the value chain. To conclude that biological platform is a sustainable platform, and to come up into the commercial level, it needs significant inputs from government with respect to policies and blending of certain extent of these bio-based material into the value chain. So that will give a way to the circular economy as well as bioeconomy significantly.
And just for me to conclude, based on this panel, I hope what can be taken away is that we have a vast array of technologies to address, as we say, the diverse array of materials that's in our waste stream. And it's really about integrating them and utilizing their benefits to help divert as much waste as we can and use it as a resource.
Great, thank you very much, Demetra and Professor Castaldi, Professor Themelis, and Dr. Mohan. So with this, we end the 2016 Global Dialogue on Waste, but before we go, I just wanted to mention that, I was a researcher at Columbia University, and research is still a significant part of my work now. And I've seen that research organizations and universities spend years together, on conducting research and producing the knowledge. We have lots of reports that come out every year, but then finally, not many people get to read these reports and then actually use these knowledge and, taking decisions or policies or moving the world forward. So, and it's also crazy to see how universities and research organizations pay to conduct the research, and then pay to get it published, and then again pay to access that published knowledge. So what we're trying to do at Be Waste Wise is start something called the Be Waste Wise Collective, where we're trying to bring research organizations together to share their knowledge and their publications through video panels on Be Wastewise as a platform. So you'll hear more about this in the coming months, but please stay updated. And thank you very much. Thanks to everyone for joining us today.
Thank you, Ranjit.
Good job. Thank you very much.
Demetra,
Thank
good luck.
you. Thank you.